Alright, this video is meant to help you solve three variable linear systems. Much like solving a two variable linear system, you basically have three options. You could solve by graphing, assuming you can graph in three dimensions really, really well. Or your better two options are probably solving algebraically either by substitution or elimination or some combination thereof. Really, you just need to find a way to whittle down and get rid of some of your variables in order to solve for one variable at a time. So for this first example, I just happen to notice that in the middle of my equations here, I've got this nice -1y. So I'm going to try to take advantage of that and use the method of elimination in order to whittle down and find my solution to my system. So I'm going to go ahead and take my first equation, and I actually like the fact that that's a 2y there, so I'm going to leave that alone. 3x plus 2y plus 4z equals 11 is perfectly good as far as that goes. Now, on the other hand, I need to change this -1y to be the opposite of 2y. So I'm going to multiply by a -2, making this -4x. Oops, and actually I want to go by +2. So let's make that a +4x minus 2y, we already have our negative, plus 6z equals 8. And if we add those two equations together, you'll notice that we get 7x, our y's disappear, plus 10z equals 19. Now, hold on to that thought, because although it is nice to have an equation that only has two variables, in order to eliminate either x or z, I'm going to need another equation that works just as well. So why don't we take our second equation, and I'm going to go down this way, and since I have a -3y in my third equation, remember, I can't recombine equations 1 and 2. I need to use equation 3. But if I can change this to a +3 by multiplying by a -3, that will make this a -6x plus 3y minus 9z equal to -3 times 4 is -12. So multiplying the entire second equation again by -3. Now let's add equations 3 and that new red equation to give you -x. Our y's are going to disappear. This becomes -4z and -13. Now we have an equation with x's and z's. Up here we have an equation with x's and z's. So how about we take our red equation, and as long as we're at it, we've got 7x here and a -1x there. Let's go ahead and multiply our equation by 7. That red equation then would turn into -7x. -4z turns into -28z. And -13 can turn into 7 times 13 is 91, so -91. Go ahead and add those two equations together, and we will end up with no x's, a -18z, and -91 plus 19 becomes a -72. Divide out our -18, and you can quickly find out that that becomes 4. The z equals 4 is 1/3 of our answer, but the nice part is now that we have these other equations with just a z and an x in it, I can plug that z back in. So again, using a little bit of substitution in order to finish off. That's back substitution, working our way backwards. So this becomes -x minus 16 equals -13. -x, if I add 16, is a 3, and x equals -3. And I've got 2/3 of my answer. And then finally, if we head back to our original equations, I can plug both x and z in. So 3 times x plus 2y plus 4 times z, which we know is equal to 4, equals 11. And it doesn't matter which equation you pick, all three equations should give you the same y value. And actually, if you try it in more than one, or you go back and check your answer afterward using a different equation, you should be able to get the same answers. -9 plus 16 is 7. Subtract that over, and y equals 2. Now, if you have a computer that can handle three-dimensional graphing or a calculator that maybe does the same, you could also go on and graph this and go ahead and check to see, oops, sorry there, and go ahead and check to see that you agree with the answer. Like I said, it's a little bit hard to see in 3 dimensions, but that point does appear to be approximately in the right place there. And it looks like our point should work. And again, if you want to write that in 3 dimensionals, -3, 2, 4 is a pretty good answer. Probably a better way to check it is, again, just take this point, plug it into your second or third equation, or both for that matter, and make sure that it makes all the equations true. Go ahead and take a second then. Here's another example of a 3-variable system. If you'd like to use substitution or elimination, that's up to you, but go ahead and try solving and see if you don't come up with the right answer. I'll pause the video now, put up all the work, and show you what the answer should be. Alright, so you'll notice I did all the work here. Took the first 2 equations. Again, I took advantage of the z here, so I multiplied the first equation by 2, added it directly to the second equation, got my blue equation right here. Went ahead and took the first equation again, added it directly to equation 3, as z minus z disappears, got my red equation. Also notice that 3 went into all the parts, so I went ahead and divided all parts by 3 using some basic algebra, which gave me an easier x to work with. Multiplied that equation by -5 in order to get the purple equation. When you added, x's disappear, got my y, divided away, and figured out that y equals 2. Then I just back substituted over here to the red equation, got my x value, took them both, plugged them back into the first equation from my original black equation up here, and got my z equal to 0. Therefore, your final answer would be 6, 2, 0. And again, feel free to take that point, plug it back into all 3 or any of the 3 original equations, and it should be a true point, a solution to the system. Now, the 2 systems here are actually special systems. They're going to be systems that show us that you can end up with either 0 or many solutions, even in 3 dimensions. The first thing I would notice is in this equation here, I've got some 2's and a 1 and a 4's and a 2. Looks to me like if I multiply that second equation by a -2, you're going to have -4x minus 4y minus 2z equals -14, which when added together basically makes 0 equals -8 when added to that third equation. Now that's an impossible statement, so therefore this set of equations should have no solution. Now how can that happen in 3 dimensions? Well, one way we could make that happen when we're looking at it is if you have parallel planes. If you notice, the red and the blue planes, looking very carefully, never actually intersect. Whereas the green equation, the green one being the first equation, just kind of crosses them both. Even though the red touches the green and the blue hits the green, never do all 3 of our planes, our 3-dimensional flat surfaces, cross. They're never going to intersect. Now, going back to this second set, looks like z would be a great thing to use on this one. So I'm going to go ahead and add my first 2 equations together, getting 2x plus 2y equals 4. If I add the second 2 together, notice the z's will also disappear there. So we're going to have 3x plus 3y equals 6. And again, I'm going to go ahead and divide by 3 here, giving me x plus y equals 2. If you divided everything up here by 2, I would actually have x plus y equals 2. And you'll notice that these 2 are the same equation. So if we went ahead and subtracted those, minus x plus y equals 2 here, you're going to have 0 equals 0 being an infinitely many solutions. And I see my spelling errors got me again. Infinitely many solutions. And again, if we take a look at our graphs there, I'm just going to turn on our infinite solutions here. You'll notice that not only do all 3 of them cross, but they actually cross in an infinite number of points. They cross on a straight line. Now, one thing you could do for that is redefine your equations in terms of one of the variables, which is not a requirement by any means, but if we define everything in terms of y right now, in fact, I'll even say that y equals a, that means that x plus a equals 2, And x would be the same thing as 2 minus a then. So x equals 2 minus a. And if we take both of those and plug them back into an original equation, that means that 2 minus a plus z equals 2. And therefore 2 plus z equals 2, and z always has to equal 0. And that would be your 3 equations solved. I hope that helps you. Again, that's just an optional portion. Remember that you can have one solution, you can have infinite solutions, or you can have no solutions depending on what type of planes you have. Good luck with 3-dimensional and 3-variable systems, and have fun.